Okay, in this video we're going to be reviewing for exam number 3. I'll be reviewing problems that you will see on the third exam, and it will cover material in chapters 6 and 7. And the problems that you see on this review sheet are similar to the ones that will be on your actual exam number 3. And also you will have a help sheet and the tables that go along with these particular problems to assist you in doing them. Okay, we'll start with problem number 1, where it says that assume that thermometer readings are normally distributed with a mean of 0 degrees Celsius and the standard deviation of 1.00 degrees Celsius. Draw a sketch and find the probability that a randomly selected thermometer will have a reading less than 0.24. Okay, so I'm going to do this on a separate sheet of paper. So here, this is problem number 1. And it does say draw a sketch, so I'm going to draw a sketch of the normal curve. Okay, so here's 0 here. And by the way, you're told that the mean is 0, and the standard deviation, of course, is 1. And 0.24 is to the right of 0. So this is the boundary line that we're looking for in that particular problem, and we're told that we want to find the probability that a thermometer will have a reading less than 0.24. Well, less than means we need to shade everything to the left of 0.24. So this is the shaded area that we are looking for. Okay. And we'll find the probability that your X value, which is your thermometer reading, is less than 0.24. We don't need to convert this to a z-score because our mean is 0 and the standard deviation is already going to be 1. Okay? And 0.24 is what we're looking for here. Now, we can go ahead and use our table A-2, which is the standard normal distribution table. And keep in mind, it is a positive value, so we look under positive z-scores here. Okay, and then we look under 0.2, which is on the left side of the z-score, and go to the right to find 0.04. And 0.04 is up here, so we read down and across for 0.024. That decimal value is 0.5948. Okay, that will be the probability that a randomly selected thermometer is less than 0.24 degrees Celsius, and that's going to be 0.5948. Okay, now the reason why we didn't have to convert this to a z-score because our mean is 0 and the standard deviation is already 1. Okay, so that's problem number 1. Okay, problem number 2 is to find the critical value for z is equal to 0.05. We're finding the critical value for z is equal to 0.05. Okay, so this is problem number 2. And here we're going to draw another normal curve. Now we're dealing with z of 0.05. That's the z value here. Now the critical value deals with a area that is to the right. That 0.05 represents this area to the right. So this shaded area represents 0.05. Now if we're going to use table A-2, we must look for the area to the left. Table A-2 requires us to use the cumulative area from the left. So if the area underneath the curve totals out to be 1, and we know that this is 0.05, then we'll do 1 minus 0.05, which is actually 0.95. Now, our table A-2 is to 4 decimal places, so we need to say 0.9500 and find out what our z value is. Okay. Well, 0.9500 is bigger than 1/2, so we need to, in this case, use the positive z-scores. Now, if you notice, that's between 0.9495 and 0.9505. But if you notice here on your table, you'll see the asterisk there. And that asterisk represents the area, and it tells us at the very bottom, the area is 0.9500, which is exactly what we're looking for. And that z value was 1.645. 1.645. That's going to be z of alpha over 2. Okay, so z of alpha over 2, or z of 0.05 would be that value, 1.645. Okay. Alright, now problem number 3. Assume that adults have IQ scores that are normally distributed with a mean of mu is equal to 100 and a standard deviation of sigma equaling to 20. Find the probability that a randomly selected adult has an IQ score between 84 and 116. Okay, so here IQ scores are normally distributed with a mean of 100 and a standard deviation of 20. And we want to find that probability that a randomly selected adult has an IQ between 84 and 116. So here's how we draw its normal curve for that situation. So here's the normal curve. And in this case, your mean is 100. Standard deviation is 20. And 84 is to the left of 100, so here's 84, and 116 is to the left, to the right of 100. Okay. Now, we're looking for the area in between 84 and 116. Okay. Alright, first of all, we need to convert both 84 and 116 into z-scores. Okay. And then we're going to use table A-2 to find the area to the left of 84 and the area to the left of 116 and subtract those two areas. Okay, so now, let's say for x is equal to 84, we need to convert that to a z-score using this formula. Z is equal to x minus mu divided by sigma. X minus mu divided by sigma, that will give us our z value. And then here, x is 84, so that's going to be 84 minus the mu, which is 100, divided by sigma, which is in this case 20. Now 84 minus 100, that's negative 16 over 20. And that will give us negative 0.80. Now here I'm rounding to 2 decimal places. So here I'm extending it to 2 decimal places. So this will be negative 0.80. and then we find the area to the left. Of negative 0.80. Okay, so here I'm going to pull up the negative z-scores for table A-2, and I'm going to find negative 0.8 on the left hand side, and that's way down here. Is negative 0.8, negative 0.8, and then 0.00 is the first column. That decimal value for negative 0.8, which would be 0.2119. Okay, so the area to the left is 0.2119. And then we got to convert a z-score for x equal 116 using that same formula. Z is equal to x minus mu divided by sigma. And in this case, your x is 116 minus mu, which is 100, divided by 20. And then 116 minus 100, that's 16 divided by 20. And that's going to give us 0.80. Okay, and then we need the area to the left of 0.80. And it's not going to be negative this time, it's going to be positive. Z-scores that we're looking at. And in this case, it'll be 0.8. And then the first column we show 0.00. In this case here, that area is 0.7881. So the area to the left of 116, that's going to be 0.7881. Okay. So now let's look at what we already have here. The area to the left here, that's the 0.2119. This area to the left, that's 0.7881. To get this area in between, which is this green shaded area, we need to subtract those two areas here to find that probability. So here, when we write this, a probability that your x value is between 84 and 116, that will be the 0.7881 minus 0.2119. And you'll end up with 0.5762. Okay, that represents the probability that a randomly selected adult with an IQ between 84 and 116, that will be 0.5762. Okay. So that represents problem number 3. Problem number 4. Assume that adults have IQ scores that are normally distributed with a mean of 100 and a standard deviation of 20. Find P4, which is the IQ score separating the bottom 4% from the top 96%. P4 represents the 4th percentile. Okay, so in this case here, to find the 4th percentile, we'll do a normal curve. So this line represents P4, which is a x value that we're trying to find. Okay. And this shaded area represents the bottom 4%. So this is the bottom 4%. Now 4% as a decimal would be 0.04. And I'm going to extend this to 2 decimal places. To 4 decimal places. So this is P4, or the 4%, or 0.0400. Okay? Now, to find that Z value that we need to go to the table that says negative Z-scores, because 0.04 is less than 0.5. And then we're going to look in the body of the table to find the number that is closest to a 0.0400. And by looking at this, I see, in this case, 0.0401. That number is closest to 0.0400. Okay? And then we read to the left and to the top. To the left of 0.0401 will be negative 1.7, and the top will be 0.05. Okay, and that's up here. Okay, so my Z value for this would be negative 1.75. Negative 1.75. Okay, but we're actually looking for the X value in this situation. So to find the X value, we use this formula: X is equal to mu plus Z times sigma. Okay. Now in this case, we've already been told in that problem that mu was 100. That should mean sigma, which is your standard deviation, was 20. Okay. So to find X, we just substitute those values in this formula. X is equal to mu, which is 100, plus Z, we found that out to be negative 1.75, times sigma, that's 20. So 100 plus negative 1.75 times 20, that you can type into the calculator, you'll get X is equal to 65. Now that X equals 65 represents the value of the 4th percentile. So in this case, we can conclude that P4 is 65. Okay. So this one, we're finding out what the X value is given a known area. Okay, and that's the approach that you'll have to take. And with these type of problems here, you have to look at the body of the table because you want to find out what that Z value is. And then use this formula to convert that to an X value. Okay. Now problem number 5 deals with the central limit theorem. And in number 5, there are 3 parts. Assume that women's heights are normally distributed with a mean given by mu equaling to 63.7 inches and the standard deviation given by sigma equaling to 1.9 inches. Part A. If one woman was randomly selected, find the probability that her mean height is greater than 64.3 inches. Then part B, if 10 women are randomly selected, find the probability that they have a mean height greater than 64.3 inches. And then part C, why can the central limit theorem be used in part B, even though the sample size does not exceed 30? Okay, so we'll answer each part one at a time. So it's problem number 5, and I'm going to start by drawing a normal curve. And with these, you want to draw the normal curve so that you can get a visual idea of how these problems are, how they look like. And in this case, mu is 63.7, and sigma is 1.9. And 63.3 will be to, I'm sorry, it says greater than 64.3, so in this case here, 64.3 will be to the right of 63.7. Okay. I don't need this mark here anymore. So 63.7 is to the right, and we're dealing with greater than. So in reality, we're dealing with this area that's to the right, shaded in green. Okay. Now, in part A of that problem, it does say, if one woman was randomly selected, find the probability that her height is greater than 64.3 inches. So we're dealing with a single individual. So in part A, as n is equal to 1, and we're dealing with x equals 63.7. Wait a minute, this should be 64.3, I'm sorry. That's 64.3. Okay, I made a mistake here. So 64.3 will be to the right of, 64.3 is to the right of 63.7. And that's the shaded area to the right that we're looking for. So in this case, we need to convert 64.3 to a z value. And in this case, it's going to be z is equal to x minus mu divided by sigma. And x is 64.3 minus mu, which is 63.7, divided by sigma, which is 1.9. Okay. And in this case here, 64.3 minus 63.7 will give me 0.6. I'm going to divide that by 1.9. And I'm going to round my z values to 2 decimal places, which will be 0. And then let you see what I just did here. I first did 64.3 minus 63.7 to get 0.6, and then took that answer and divided that by 1.9. Now the 2 decimal places, that's going to be 0.32. Okay. Now, I need the area to the left of 0.32. Okay. And it is a positive z-score, so I need the one that says positive z-score. And find 0.3 and then 0.02, which is up here. So 0.3 going across, and then 0.02 going down will be 0.6255. Now keep in mind that 0.6255 represents the area to the left, which I don't want. I want this shaded area to the right. That says greater than is the shaded area to the right is what I'm looking for. So in this case here, I need to do 1 minus 0.6255 to get the probability that x is greater than 64.3. So it'll be 1 minus 0.6255, and that should give me 0.3745. Okay. Yeah, 0.3745. Now that represents a probability that a single woman randomly selected that would have a height greater than 64.3 inches will be 3.3745. Okay. So that's part A. Okay, now part B states if 10 women are randomly selected. Find the probability that they have a mean height greater than 64.3 inches. So we're dealing with 10 randomly selected women. So here's the B part. N is 10. 10 randomly selected women. Okay. And in this case, our X is still going to be 64.3. But here, we're not going to use this Z formula here. We're going to be using a different Z formula. And that Z is equal to X minus mu divided by sigma over the square root of n. That's the formula we use for a sample size that's bigger than 1. And in this case here, we're going to substitute those same values here. Your X is still, now this time X bar, because we're dealing with the mean height. So you don't want to leave that off. X bar was 64.3 minus mu, which was 63.7, divided by sigma, that's still 1.9, divided by the square root of n, or the square root of 10. Now, in this particular situation here, if you do this in the calculator, you want to make sure that you put all of this, the numerator and the denominator, in parentheses. Okay, so here's how we're going to do this in the calculator. I'm going to include this out. You start with left parentheses 64.3 minus 63.7 and then close the parentheses. Then divided by, and then left parentheses 1.9 divided by square root of second x squared for the square root, and then type in 10. Close the parentheses for your square root, and then close it again. Now, for those of you who have the TI-84 Plus, you'll use your right arrow key to get out from underneath the radical symbol, and then close your parentheses. Okay? And then you hit enter. Now, this will be to 2 decimal places. So 0.998 will be this number, 1.00. Okay? 0.998. Because the second digit after the decimal point is a 9. Next to it is an 8. So 99 will increase to, well, 0.99 will increase to 1.00. So my Z value is 1.00. Okay, and then we use table A-2. Find 1.0 on the left and 0.00 up here. That's the first column. 1.0 and 00 will give me 0.8413, which is the area to the left. So in this case here, the area to the left is 0.8413. But I don't want the area to the left. Let's go back up here. I want the shaded area to the right. Okay? Because the table gives me the area to the left. To find the area to the right, you have to do some subtraction. So here, when I write this, the probability that the mean is greater than 64.3, that will be 1 minus 0.8413, which will be 0.1587. So in this case here, the probability that 10 randomly selected women will have a mean height greater than 64.3 inches would be 0.1587. Okay. Now to answer part C of number 5, Why can the central limit theorem be used in part B, even though the sample size does not exceed 30? Well, we were told in the problem that we're to assume that women's heights are normally distributed, which is one of the requirements that would allow us to use the central limit theorem. We're told that we have women's heights that are normally distributed. Okay, so in part C, we can just say that women's heights are normally distributed. And that's all you can just say right there. Because of that, it allows us to use the central limit theorem. So that was problem number 5 right there with 3 parts. Okay, on to problem number 6, which deals with confidence interval estimates. And in problem number 6, it says here, a clinical trial tests a method designed to increase the probability of conceiving a girl. In a study, 642 babies were born and 321 of them were girls. Use the sample data to construct and interpret a 99% confidence interval estimate of the percentage of girls born. And you're going to round to 3 decimal places. That means you're going to round your confidence interval limits to 3 decimal places. Okay, so now let's look at what we were given. We were told we got 642 babies that were born, that's your sample size, and 321 of them were girls, so we're letting X be the number of successes, which is 321. Now we're given N and we're given X. So to find out what P hat is, that's the sample proportion, we take X and divide that by N, which means we take 321, divide that by 642. Now 321 divided by 642, that would give you a decimal of 0.5. Just type in 321 divided by 642, you should get 0.5 as P hat. Well, if P hat is equal to 0.5, then Q hat, that's simply 1 minus P hat, or 1 minus 0.5, which is 0.5. Because Q hat is the complement of P hat. Okay. Now we're dealing with the 99% confidence interval. If we have 99% confidence, there is a table that I gave you in class that tells you what your critical Z value is for each of the most common critical values here. For 90%, it was 1.645. For 95%, it was 1.96. And for 99%, it was 2.575. And since we're dealing with a 99% confidence, that Z value is 2.575. Okay. And by the way, that table will be on your help sheet. But you just want to be familiar with just the 3 most common critical values for your confidence intervals. 90%, that critical value will be 1.645. 95%, that critical value will be 1.96. 99% in this case will be 2.575. And then we can use that to find our margin of error, because we're going to need that to construct the confidence interval. Now the margin of error has a formula, which is C of alpha over 2 multiplied by the square root of P hat times Q hat divided by N. And we just substitute those values here. That's C of alpha over 2, which is our critical value for a 99% confidence level. That's 2.575. And that's going to be multiplied by the square root of P hat was 0.5 times Q hat, which is also 0.5, divided by N. N is our sample size at 642. Okay, and then we can type all that into the calculator. So in this case, we will type in 2.575 times the square root second x squared for the square root 0.5 times 0.5 divided by 642. And then hit enter. And I'm going to round this off to 4 decimal places. I'm going to round this off to 0.0508. That's going to be the margin of error. 0.0508 will be my margin of error. Now, since I have the margin of error, and I do have my sample proportion, which is P hat, I can go ahead and construct the confidence interval. And the format for the confidence interval for a proportion is P hat minus E, that's less than P, and less than P hat plus E. And then just substitute those values here. P hat is 0.5 minus E, which was 0.0508. That's less than P and less than. Copy those same numbers, but this time it's going to be a plus sign in between it. 0.5 plus 0.0508. Now, if you subtract 0.5 minus 0.0508, you're going to get 0.449. And that's rounded to 3 decimal places because we're told to round our confidence interval limits to 3 decimal places. And then on the right side, 0.5 plus 0.0508, rounded to 3 decimal places, that would be 0.551. Okay? So that's our confidence interval. Now, to interpret that confidence interval, we have to write a statement for that. And the way we write the statement is this. We say that we are 99% confident. We are 99% confident that the true percentage of girls born lies between. Now, these confidence interval limits I'm going to change to percent because it says true percentage in this case. So 0.449, if I change that to a percent, it will be 44.9%. And 0.551, change that to a percent, that'll be 55.1%. Okay. So that's how you would write and interpret the confidence interval estimate for the percentage of girls born. And in the problem, it does say percentage, so you have to change your, on your limits, you have to change your your decimals to percents. Okay. So that's problem number 6. Problem number 7. You're finding the sample size required or needed to estimate the percentage of adults who have consulted fortune tellers. And here you want to use 0.08 margin of error and use a confidence level of 90%. And you want to use the results from a prior poll suggesting that 18% of adults have consulted fortune tellers. Okay, so here we're finding the required sample size needed. Okay, so let's look at what we already have. We're told to use a 0.08 margin of error, so that means your E is 0.08, and use a 90% confidence level. And that's one of our three most common confidence levels here, so we should know what that Z of alpha over 2 is going to be, that critical value is going to be. For 90%, it is 1.645. Okay, that's one of your three most common confidence intervals. For 90%, that critical value is 1.645. 95% will have a critical value of 1.96. 99% will have a critical value of 2.575. And we're also told that we're to use the results from a prior poll suggesting that 18% of adults have consulted fortune tellers. So here, P hat, that's 0.18. 18% as a decimal will be 0.18, which means that Q hat, that's 1 minus P hat, or 1 minus 0.18, that will be 0.82. Okay, and there's a formula that we use. Since we already know where P hat is, we use this formula. Z of alpha over 2, which is a critical value, and that's squared, times P hat, Q hat, all over E, and that's squared. Now your Z of alpha over 2, that was given to you as 1.645. And that has to be squared. Times P hat is 0.18. Times Q hat, that's 0.82. All that's divided by E, which is 0.08, and that's going to be squared. And all of this is going to be entered into the calculator. Okay, so the numerator will be 1.645, and then we square that, times 0.18 times 0.82, and then that's going to be divided by 0.08, and then that's squared. Then hit enter. Okay. Now in this case, this is 62.4. Now, when we're finding the required sample size, the round-off rule is this. We always round up to the next larger whole number. If your value of n is not a whole number, we round up to the next larger whole number. So we're going to round 62.4 up to the next larger whole number. That will be 63. Okay, so that means the required sample size, n, will be 63. Because that's what we were looking for, the required sample size. Okay, now again, when you're doing the required sample size, if your n is a decimal, then you round up to the next larger whole number. Okay, and finally, problem number 8 is a confidence interval about a mean. The First National Bank is considering a survey of its customers to estimate the mean number of checks written per month. A sample of 36 customers was selected with a sample mean of 33.4 and a sample standard deviation of 11.2. You want to construct and interpret a 90% confidence interval estimate for the mean number of checks written. Okay. Alright, so let's look at what we're given in this problem here, problem number 8. Just identify what's given. We're told that our sample size is 36, so that's your N. Because we have a sample of 36 customers. And then we have a sample mean of 33.4. Your sample mean, of course, that's X bar, 33.4. And the sample standard deviation, which is lowercase s, that's 11.2. So you got 3 pieces of information given, actually 4. Because we're told to construct and interpret a 90% confidence interval. Now, in this case here, we're going to be using table A-3, which is the critical t values, because we're dealing with a population mean where the population standard deviation is not known. Okay, that's very important here. We're dealing with a estimate of a population mean where the population standard deviation is unknown. Now, on your table, under area in 2 tails, you will see the area in 1 tail and the area in 2 tails. With a confidence interval, you always use the area in 2 tails. Always, for a confidence interval. And in this case, these are your alpha levels here. So to find your alpha level, you always do 1 minus whatever that confidence level is given to you. Okay? Now in this problem, we're given a 90% confidence. So that means your alpha level will be 1 minus 0.90. which is going to be 0.10. And also, we need our degrees of freedom if we're using table A-3. Your degrees of freedom is always n minus 1. N is 36, so 36 minus 1 will be 35. Okay? So we're going to use these 2 pieces of information, our alpha level of 0.10 and the degrees of freedom of 35 to find our critical t value. So here's table A-3. On the left side, under degrees of freedom, you find 35. So here's 35 right here. And we need to find, in this case, 0.10. Okay, and I'm going to need to pull this down a bit. 0.10 is under the area in 2 tails. You always look under the area in 2 tails. So that's your 0.10 here. So you have to look down that column and go across the 35. And it's going to be this value, here we go. It's going to be this value, 1.690. Okay, you have to look under area in 2 tails for your confidence interval. Okay, go down and across, that'll be 1.690 under 35 degrees of freedom. So T of alpha over 2 is 1.690. Okay, and now to find the margin of error, that's going to be T of alpha over 2 times S over the square root of n. And then just substitute those values. T of alpha over 2 will be 1.690 times S, that's your 11.2, over the square root of n. N is 36, that's square root of 36. Now all that we can type in the calculator. So in this case here, we type in the 1.690 times 11.2 divided by, for the square root, second x squared, and then 36, close your parentheses, or use your right arrow key if you have the newer version of the TI-84 Plus calculator. Let's say I want to round this off to 3 decimal places. That margin of error to 3 decimal places will be 3.155. So your margin of error in this case will be 3.155. Now, I have my margin of error. I do have my sample mean of 33.4, so I can go ahead and use the format for the confidence interval estimate to construct that confidence interval. And that format is this: that's x bar minus e, and that's less than mu, less than x bar plus e. My mean was 33.4. So that's 33.4, or sample mean was 33.4. The margin of error was 3.155. That's less than mu, less than x bar is 33.4 plus 3.155. And in this case here, if I do 33.4 minus 3.155, now here we round our limits to 2 decimal places because the sample mean is to 2 decimal places. So when I subtract this, I'm going to round this to 30.2. And that's less than mu, and less than 33.4 plus 3.155 will be 36.6. Okay, so that is my confidence interval for a population mean, where the population standard deviation is unknown. Now we're asked to interpret that, so we need to write a statement that does interpret this confidence interval. So our statement is this: that we are 90% confident that the true mean number of checks written lies between 30.2 and 36.6. And that's all you have to say on that particular interpretation of that confidence interval. We are 90% confident that the true mean number of checks written lies between 30.2 and 36.6. Okay, so that will be basically what you're going to see on exam number 3, which will be on Monday, November the 3rd. Okay, please feel free to email me if you have any particular questions about any of the problems that are presented in this video, because they will be similar to the ones that will be on the actual test covering chapters 6 and 7.